Thanks for coming, everyone. We're going to talk about robust stream processing with Apache Flink today. Before we get started, quick background. I'm Jamie Grier. I'm the Director of Applications Engineering at Data Artisans. Data Artisans is the company, everyone hears me okay? Yeah. Data Artisans is the company that formed around Apache Flink. It's co-founded by some of the original creators of Flink. Little background on me, I've been working on stream processing of various forms for most of my career. I did work here at Twitter for a little while on the streaming compute team and on some other things. I also worked at a company called GNIP, which is like basically a big stream processing engine is the core of the company. And before that, I was working on like ultra high speed video processing, which is a bit different, but still a lot of the same kind of algorithms and stuff. So that's kind of what I've been doing most of my career. What we're going to talk about today is, first of all, just a super quick introduction to Apache Flink. We're going to move real quickly through this stuff. We're going to talk about what is stateful stream processing and how is that different from kind of the previous generation of stream processor. We're going to talk about windowed computation over streams. The reason that's interesting is because if you have an infinite data stream and you're doing something like just some simple statistics like group by key and count, obviously you can't compute a sum over an infinite data stream unless you window it. So you have to define things like windows and stream processing. It's something that comes up all of the time. So you have to be able to handle that stuff properly. Then we're going to kind of get into a little bit of the meat of the talk. So we're going to talk about robust time handling. We'll get into a little bit the idea of event time versus processing time and what that means. We're going to talk about failure handling. So in the context of stateful computation, not just simple like stateless services, but in the context of stateful computation over streams, how do you handle failures? A much more challenging problem when you have state. We're going to talk about then how do you handle like production-oriented issues like planned downtime, upgrading your job, upgrading the cluster, upgrading Flink. And then finally, also we're going to talk about like reprocessing data. So this is something that if you're really running things in production comes up all the time, where you need to return, like say you discover you're interested in some new aspect of the data stream, or you found a bug in your code and you want to back up to some previous time and reprocess all the data from there. That should be, A, you should be able to do it correctly, and B, you should be able to do it fairly easily. So I want to demonstrate how that works in Flink. And think about, as we're going through that, we'll talk about, things get a lot more challenging when you're doing stateful computation. So if you're going to back up to some previous state in the system, there was no point in time when like sort of you're at the zero state, except for maybe a year ago when you first started this job. Everything else is stateful computation after that. So if you're going to go back and reprocess data, you need to go back also to a consistent previous state and reprocess data from there. So pretty challenging to do if you don't have the right tools. So we're going to talk about that. Okay, just for reference, are there many people in the audience that have heard of Apache Flink so far? Okay, so that's pretty good. And is there some general familiarity with stream processing with other frameworks and stuff? Okay, cool. That makes it a little bit easier. In general, Flink is an open source platform for distributed stream and batch data processing. Most people probably don't know this about Flink because everyone's really interested in the streaming space these days, but Flink was actually created as kind of the idea of the project. This was 5-6 years ago at the Technical University of Berlin. The idea was, what if we apply a streaming data flow engine to big batch processing, right? And the reason to do that is because rather than like, if we simplify the problem and just think of map and reduce, rather than like have all your mappers run and then they generate a pile of data and then have all your reducers run, it's a lot more efficient in terms of use of hardware and like the end time to compute some job if you actually pipeline the shuffle between the mappers and the reducers. You don't map and then reduce. The reducers start to run as soon as the mappers start, right? As soon as the mappers are producing data. So that's applying a data flow engine to this batch processing idea. So that's actually the genesis of Flink from years ago. But it turns out if you've already built a streaming data flow engine, guess what? It's super good at streaming data. It's a great choice for an architecture. So These days, most of the focus in Flink is around stream processing. That's kind of at a high level view, not a super interesting diagram, but a super high level kind of what it looks like. The main point is that the core is the same. It's a streaming data flow runtime. There's the data stream API on top of it, which is kind of like the stream processing API. Or to get more clear about this concept, it's an API that allows you to deal with unbounded data sets, right? Data is continuously being produced, and you have a continuous computational model over the data. That's the data stream API. The data set API is when you have a bounded data set, and you want to do things. The APIs are very similar, but in the data set world, because you know something about bounds on the data, you can use some different algorithms if you're doing big joins and things like that, like a typical batch processing workload. But APIs are slightly different, very, very similar. If you can use one, you use the other, and the runtime engine is streaming data flow engine no matter what. Just with some different algorithms plugged in around joins and things like that to make it a good batch processor. What we're going to talk today about today is really the data stream API, because that's really what gets most of the attention and focus these days. Layered on top, there's also a complex event processing library. You can think of that as like basically a state machine over streams. So you have a stateful stream processor. It's really nice and easy to build correct state machines that are still correct in the face of faults and everything. So it's a great CEP engine because of that. And then there's a relational API. There's actually missing from this diagram, there's a SQL API now, so you can express your streaming programs as SQL. Machine learning, graph processing, and then on the batch side, there's also a table and relational API. The core of the technology and what gets the most focus and development in the project is really these APIs and runtime, and then there's these other projects also on top. But the real technology is in yellow, in my opinion. Oh, and then of course on the bottom, there's just a lot of different ways you can deploy Flink, and this is a little dated. You can deploy with Docker, you can deploy with Kubernetes, Mesos, Yarn. You can have a standalone Flink cluster as well if that's what you want to do. And there's the Yarn support is really good already. Like it's you just, hey, I've just got this job, run on Yarn and everything just works. Running on Mesos or with Docker takes a little bit more effort from you, but people do it all the time. And then you've got coming really soon in Flink 1.2, which is several weeks out from now, there'll also be first-class Mesos support. So you can just like, hey, this is my library, run this on Mesos somehow, and it just works. Uses Mesos to acquire resources and everything else. Okay. This next little section, it's good that there's a lot of experience in the room. This is going to be the world's quickest introduction to stream processing. And then we're actually going to, for the rest of the time, we're going to write code and like demonstrate things. And it's going to be not too many of these slides. But what the heck is stream processing? This is the simple version. You've got a data stream, which is an infinite data set. Data is just continuously being produced and arriving all the time. It's unbounded. You've got some code that you want to run, some kind of computation you want to run over that data stream. And then you want to produce some sort of output as another data stream, often as another data stream. Not strictly necessary, but yes. So that's kind of the model of early stream processing, and you hook a lot of these things together, and you get these topologies of these streaming operators, and you can build kind of cool stuff this way. However, what's missing from this picture, what's missing from this picture is state. If you don't have any state, and you can't do stateful computation correctly, you can do really simple things like ETL and filtering and maps and those kinds of things, but you don't really have a full computational model. So stream processing becomes a lot more interesting when you have state, right? Same basic model, consume infinite data streams. You've got some code here, but that code can keep track of state. So now your output can be affected not only by the current input message, but all messages you've seen before. This, if you think about it, this is equivalent to, like, imagine if we had to write code with no memory, with machines with no memory, right? If you want the thing to sort of function correctly, you can't really have state because sometimes you just lose it. It's a pretty uninteresting programming model. This is a full programming model. You can build anything you want with this. And we'll talk about, and I'll show you, as long as that state is fault tolerant, even when you distribute it across lots of machines, you can build anything you want. So that's what stateful stream processing is. By the way, if we're talking about state, just to put something concrete here, if you're doing something simple as consume a stream, group by key and count, that's stateful computation, right? The current count for every key is the state. If you don't manage that state fault tolerantly, you can't even do sort of distributed counting, not correctly, right? So you really need state for stream processing to be truly interesting. Okay. Slightly more complex example, like I said, you've got sources of data streams on the left, sinks for data streams on the right. You know, RabbitMQ, maybe HDFS files, maybe Kafka. You're doing some things in the middle. Here's a stateful aggregation, then you're writing to a database maybe at the end. That's like a really typical stream processing topology. This computation in the middle can be anything. And then we don't just want one thing like this, but we want to use loads of machines, distribute this stuff across loads of machines, and process like this at scale. So that's what Flink is for. That stateful computation model over streams and running at very high scale. You can do all of those things with Flink. That's kind of the point. Benchmarks are what they are. Take it for what it's worth, but I did some benchmarking, which is basically the typical analytics workload. Consume a stream, group by key, and then do a windowed count for every key. And on 10 machines with 40 gig interconnect, because often Flink will just saturate the network, that becomes the bottleneck right away. So when you got to the point where I had 40 gig interconnects between all these machines, I was able to run 72 million messages per second on these 10 machines. So it's super efficient. Right? And think about this, if you think about this group by key, that means full shuffle of every message across the network, right?
How light of a record or how complex is the computation?
It's just a simple computation. The whole idea is to sort of measure what the stream processor can do, right? So what's important in stream processing is essentially parallelism. Group by key is super important because that means you can repartition the data as needed. So that's like the big shuffle over the network. And then in this case, a windowed count. So for every key for this hour, what's the count, right? That's the computation. Pretty simple. It's a real standard sort of analytics type application, but yeah.
Group by key isn't recommended for batch processing. Is that different for stream processing?
I wouldn't say that actually. So like if you just wanted to know, you know, for each of my ads, how many clicks per hour, that's group by key. So
you don't really have to worry about data skew.
You do, yeah. Whenever you do stuff like that, partition by key, you do have to worry about data skew. But yeah, none of that changes in stream processing. It's the same. It's the same, yeah. Okay. And now we get to the meat of the talk. And we're going to actually just write some code. This is where it's more fun. Okay, so this is sort of like a total stub of a Flink job. It's just a main method. You get an execution environment. I set the parallelism to 1 because it's easier to reason about this during demo, so you'll see why. And then I'm going to execute the program. All right? This is the stub of a Flink job. You can get started with Flink just like this on your laptop. You don't have to install anything. You don't have to download Flink. You can actually just take a Maven dependency and start writing code like this. And when you run this thing in your IDE, it'll spin up a cluster, an embedded cluster, and actually execute your program on the cluster. So you could all probably, if you wanted to, you could all be like writing Flink programs 5 minutes from now. Super easy. Okay. So we're going to define a stream. I'm going to cheat a little bit. I have a data generator to make things simple. And I'm going to simply, so you can see what the data is like, I'm just going to print, whoops. And I'm just going to show you what the data looks like, and then explain a couple things, and then we'll go from there. Okay. Can you guys actually see this in the back? Okay. The data is super simple. It's a timestamp, some key, in this case, temp, pressure, or door, and some value. The idea of this exercise is that these are sensors, maybe IoT sensors, whatever. You've got a door sensor, which is going to be like an open-close thing, a temperature sensor, and a pressure sensor, which are going to be just sort of analog waves, right? So that's kind of what the data looks like. It's probably a lot more interesting to see it visually, so that's what we're going to do with it next. Take that same stream, and we're going to add a sync to this job. And we're going to, write it to influx. And we're going to take a look at that. If you're not familiar with influx, it's a time series database. It's got a really nice flexible data model, which I like a lot. I don't have a ton of experience trying to use influx at any reasonable scale, but for these demos, it works great. I actually like the data model a lot. And the cool thing about influx is we can sort of just put Grafana on top of it and quickly be looking at the data, so it's kind of nice. Okay. So you've got a temperature sensor, pressure sensor, and a door sensor. That's what the data looks like. It's all coming in as like one stream of data, and then we're partitioning it by key and graphing it here. Okay? So that's what we're looking at. And then we're going to do something a little bit more interesting with this. What we're going to do is build this. So a really common pattern in stream processing, and it's also a good thing for a demo because it's very obviously stateful. It's easy to see what the state is this pattern where you have like the main data stream and a control stream. You're going to join these two streams together. And there's going to be state. I'm going to explain to you what that is, and then there's an output stream. So I'll give you an example. Say you had a topology that was filtering data, right? But you want to sort of dynamically control what all the filter rules were. So imagine this is ad clicks. And this other stream says, hey, some user writes into this stream, I want to see information out the other end of this filter about this set of ads, this set of ad IDs. So this is the main data stream. This is a stream of essentially rules that we're going to use to update this computation here so that we're sort of dynamically controlling it using the state, and then we're going to have output. In the case of our example, that's like more real world. In the case of this example, these are those waves. This control stream is going to be, it's going to allow us to control the amplification factor for each of those keys individually, and then we're going to have output. I'll show you, it's going to make more sense in a second. But this is a really common pattern in building sort of interesting dynamic stream processing applications. And the way you do this in Flink is going to be, first of all, I'm going to add this second stream. Oops. For this one, I'm just going to read from a socket, which is that in Flink. And I'm going to actually, you can see, let's see, let me blow this up. So that I can sort of control, I'm going to type messages here. So I can control for each of these sensors what the amplification factor should be. And we're going to literally be able to dynamically change our waveforms. So I've got this control stream now. Just going to read in from that socket. Next thing I'm going to do is sort of essentially parse the message. Now I've got a stream of control messages. By the way, everything is strongly typed in Flink. So what's the type of this thing? Data stream of control message, right? If I did another map step here, something like, then the type here is going to be string. that make sense to everyone? So Flink is strongly typed all the way through. You use your types. You don't have to use like weird, you can use tuples and stuff, but you don't have to do that like some sort of big data frameworks. You actually use just like strongly typed all the way through. And also, because we're using Scala here, we don't need all this cruft, which I love. And we can go back to this cleaner looking thing. Okay, so we have this control stream and we have the original stream. What we want to do is, I'll come back to this keying. We want to connect the two. And we're going to connect and then from there, we're going to execute some function. And then we're going to add this. We're going to add a sync. Again, we're going to write to influx. Going to give it another name. And that's pretty much it. So what we've done is we're reading the main generated data in the real world. Maybe that's coming from HDFS or Kafka, really often Kafka. We're going to write that raw data out just as it is. We're also going to read a socket as a stream. I'm going to read from localhost and parse the message. So now I have these two typed streams. I'm going to partition by key, and I'm going to partition the control stream also by key. So at scale, if you think about this, you're consuming all this fire hose of data. You group by key. That's really sort of, in a sense, a routing function. So all the keys with the same value end up going to the same host. I key the other stream exactly the same way. So all the interesting data, if I want to keep state per key, if I key both streams the same way, they can share state. Does that make sense to everyone? More or less? So really what you're doing when you're doing this step, and then updating state, you're creating kind of in the stream processor. You can think of it like a distributed key value store that's sharded on the key. You shard the stream on the key, and you shard the state or the other stream on the key, and all the stuff that kind of naturally goes together ends up on the same machine. So you can do things like aggregations, stateful computation, all that stuff. But you've got a sharded state store throughout the stream processing topology. Okay, so you can build a lot of cool stuff with that. But so we've connected the two streams. This stream keyed by, this stream keyed by, connect the two, and apply this function. So when we run this guy, you see down here, same waves as before, but we also added this is the output of that amplifier function that graphically looks like that, right? That's what we just built, exactly what we just built. And now I can do things like set the amplification factor per key. Okay? So I just dynamically changed the output. I sort of programmed my amplifier function dynamically. And there's state held per key, which is this amplification factor for every key, or for every sensor. Is everyone with me?
Where is the state information stored?
The state information is stored locally throughout the stream processor, right? Exactly that kind of key by function also partitions the state, right? So you can scale horizontally.
On Unix disk or HBase or?
So it's stored locally. There's a number of different ways. It can be just stored in RAM. It can be if you want to get bigger than that, you can spill to disk. It happens to use as an implementation detail, RocksDB. It's not important at all. It's just a way to spill from RAM to disk. But for it to be fault tolerant, you have to make snapshots. We're not going to have a ton of time, but maybe we have time at the end to talk about how the fault tolerance mechanism really works. I'm going to show you how it works, and I'm available after too. But it does this thing called lightweight asynchronous distributed snapshots. and Flink makes essentially snapshot copies of all of the state of the whole computation periodically. And it does that in such a way that it doesn't interrupt the data flow and it doesn't introduce any latency. And what you can get from that is actually around all this state that's being computed in the stream processor, you can get exactly one semantics. It doesn't mean exactly one's message delivery. What it means is that the state you're computing, right? So if you're counting the counts for every key, you can compute that state correctly even in the face of failures. It's as if, the result will be exactly as if each message was processed exactly once. So that's what's called exactly once guarantees in stream processor. What's that?
If you input door 10 right now, what happens?
This key will just have a new state, and the
Two keys on the connected side, or are those combined?
let me show you how the function works. I think maybe it'll be more clear. So that's door. If I say door 10, see, just changed. So I literally for key door, I'm now storing a value that's 10, and that's the yes. Yeah. In this case, because that's the topology I built, right? That's how I designed it.
Do you checkpoint the state after every event? Or
No. No.
So in case of failure, how does it recovers the
Yeah.
events it has processed?
I think we should totally talk about it at the end. It's probably the most interesting thing about Flink, but it doesn't really fit in the context of the rest of this. But at the end, I'd be happy to talk about exactly how it works. Okay?
So this graph is by influx dB, right?
What's that?
This graph is by influx dB, right?
The graphing, the nice dashboard is Grafana, and it's backed by Influx DB. Yeah.
So in Flink, it doesn't have the notion of like micro batch as
No.
right? It's like storm.
It's completely continuous processing. Yep. There are no batches of any size. Yep.
just event by event.
Event by event.
Can you show the code of the function?
Yes, let's do that. Thank you. Okay, super simple. Okay, this is the amplifier function. Connect and flat map, right? We connected them, and then we have a flat map function. This is sort of like the left-hand side and the right-hand side. This is the control stream. We saw how it was all typed, right? The control stream and the main data stream, which is just of this type data point, which is not a Flink type. That's just my type for the demo. Okay? So all we're doing in the control stream is we're getting state called the top line here. That's a state descriptor. It's called amplitude. That's just a name I made up. It's got type double. And Flink will manage that state for you. This is an example of using, that state can be anything you want as the user. This says get that state and update it with the amplitude from the message, right? So we just updated our state. Super simple. When we process the data stream side, because we've connected the two, we process the data stream side. When you get a message on the data stream, you get the current state, which is the amplification factor for the key, and you say, multiply, right? That's the whole amplifier function. But the point is it's completely stateful, and it's distributed and partitioned at scale. So this will work if there's 100 million keys. Yep.
I'm not sure I understand flat map 1 and flat map 2. Flat map 3.
So you understand flat map?
Yeah.
The fact that it's a connected stream, it's a way to process continuously on over both of those streams. The whole point of connect is really that you can share state between the two. So that's kind of that input, the control message side and the other side. And no, there aren't 3 and 4 and 5 versions. I think in a future version of the Flink API, there will be something like that, but it won't be static like this. You'll use annotations to, so it'll be a lot more flexible.
So can you extend this real quick to make it so that the amplitude is added to the previous? So you can put 4 and 10, but 10 overrides the previous 4. Can you just make it go to 14?
You can do whatever you want. It's just it's a full stateful computation model.
Just to show the code real quick.
So you want to do,
So the amplitude,
You want to keep 2 values for every key?
No, the amplitude builds on the previous.
Okay. So you want to, you've just queried this line, get the current state, right? Line 21.
I think he's saying when the control message comes in, rather than overwriting the previous value, you want to add to the previous.
On the control value side? Okay. So you have, you want to do that, and then you want to do yeah, I did jump to Java. That's true.
Live demos are way more fun.
That's the old value. Then what? You want me to mix the two somehow?
It's just old plus F.
That?
Okay.
Yeah.
This is the easy case of getting the previous state of myself, but you can also get the previous state of the other.
Yeah. This is a query. It's exactly the same as this. That's a query, right?
So what are the guarantees about that query? Can it end up doing some sort of I/O to an external system, or is it always going to be cached within the string node?
It's Flink state. So there's a such thing in Flink as a state backend, right? And they're pluggable.
Okay.
So it just depends on the state backend exactly where that comes from. But the point is Flink actually controls it and can guarantee the semantics around it. That's why it has to be a first-class citizen in the API. Flink has to understand state. It's the only way I can make it fault tolerant for you. Let's. What's that?
Regardless of how many machines, this is distributed over as global.
No, exactly not. So you want to partition it, right? So you key by, partition everything, right? And so you can scale horizontally. And so you partition the stream and you partition the state as well. You've deployed these operators across like 100 machines. There's local state on each one, right? Sharded by key. I think we have to move on. We can save time at the end though. There's a lot to cover. It gets more interesting than this. Okay, so that's this program running, right? The other thing I said it was really common to do in stream processing is windowing. This has got to be done correctly because you have to do it all the time. Most interesting applications have windows somewhere. So I want to do a window too, so you can see how it works. So let's add one more thing. Again, we'll take that stream. Key by. And then let's compute a time window. And then compute, and then have a reduce function. And then once again, we're going to write it to influx so we can take a look at it. We're going to call this the summed sensors. Okay, makes sense? That's a super common type of analytics things to do. It's that many lines of code because kind of Flink gives you those primitives. So consume, group by key. So for every key, compute a time window and then reduce over that window and compute something, whatever you want here. I happen to just be summing things up, and then I'm going to write it to influx.
Is that a sliding window or chunk?
That one is a tumbling window. Okay. There's also sliding windows. Tumbling means, it's every second. Sliding means they overlap. So you have if I add a second parameter here, I can also add a second parameter here with a slide time. So compute over the last hour, sliding every minute, whatever you want. You can also do session windows, which are totally data-driven, which is imagine typical website user session tracking. User comes to the website, a session starts, they click around for a while, some period of time goes by that's completely indeterminate, but they're not active. And then you sort of say, okay, that's a window, and then you compute analytics over it. By the way, something that's almost completely impossible to do correctly with a batch processor or any kind of mini batch system, because the window is completely indeterminate with regard to any kind of boundaries. So easy, super easy to solve in real stream processing, really hard to solve any other way. So you have session windows, you also have custom windows, so you can actually decide how things should get windowed, when to trigger output, all that stuff. So this is kind of like the highest level of the API, but it gets more advanced. Okay, so let's run this and see what happens. 5 minutes. See, too many questions. We have a lot to cover, so I'm going to go really fast now. Okay, so let's see what's going on. This is interesting. I'm doing a sum over the middle one's the pressure sensor is a sine wave. It's a perfect sine wave. It's aligned on second boundaries. Its period is 1 second. I'm computing a sum right here. What should the sum over a sine wave be over its period? Anyone? 0? Should it be approximately 0? Or should it be exactly 0? Exactly 0. Does anyone have any idea why that's not exactly 0? Any guesses? What's that?
Is it because it's double and there's something?
It's not exactly the period.
Exactly. Exactly right. This is exactly the difference between processing time and event time, one of the things, and why it matters so much. What we're doing here is really naive. We're actually just drawing windows based on the wall clock time of some machine, and we're throwing data in that window, and then like when the window's done, we compute some result, and that's the answer. But sometimes data is delayed, it comes late, it comes in bursts, it's backed up in Kafka, it's backed up in Flume. By the time it gets here, God knows what it is, and we're just kind of using machine time to like compute stuff. Not very smart. And second thing is, like say, what if we want to rip through like a whole bunch of historical data? Like the value here is approximately 4.5, right? If we rip through a bunch of historical data at 500 times the speed, we don't want this to be 4.5 times 500, and that's the sum we compute. That's processing time, and it's a very sort of inaccurate, naive approach to stream processing. This is what we want to fix. I don't think there's anyone in this room right after us. If we go a little bit long, we have a little extra time. This is what's happening. The green is the timestamps. What we want to do is draw windows like this by looking at the data, and we want to do this exactly correctly. And what we're actually doing is sort of drawing the wrong windows because we're not looking at the timestamps in the data. We're just kind of like doing it on the clock on the machine. So that's what we're doing. That's what we want to do. And by the way, we want this to happen no matter when the data comes in. We want it to happen no matter if the data is totally misordered, right? Because it always is in the real world. The data is totally misordered. We still want to window it correctly regardless of the fact that it's coming out of order. That's what event time is all about. It gives you this repeatability and determinacy and correctness. And that's why event time is so important if you're doing anything like analytics or you want your computation to just be correct and repeatable. You definitely need it. So to fix this in Flink, we're going to do the following. Stop the previous job, run this job, see what happens, and let's see if we get exactly the right answer. Okay? Here's some interesting, whoops.
So effectively, you modify it to go by sample count instead of time?
Yeah. What I've done, I think the best way to think about this problem is you've got this unordered mess of data, but you've got timestamps in it. It's completely out of order. But what you want to do is take the data, and from just the data, extract a clock, a disciplined, well-mannered clock that advances monotonically from this unordered mess, right? So the data itself drives the clock, and then everything you do with time, you use that clock. That's kind of like, I don't know, in engineer speak, that's, I think, the best model for thinking about it. So now if we just run through data at 100 times the speed, doesn't make any difference. It's just a clock, tick, 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 tick. And if the data is unordered, assuming we can build that nice clock from unordered data, which you can in Flink, you get the same property. So then anything else we do in the computation that has to do with time, we use that clock instead. So that's how it works.
How do you address parallelism to get that consistent clock?
At the end. That's another really cool thing. I think the two things in Flink that are super cool as the base technology are how do you do that? How do you generate, it's called watermark generation, and how do you like create global time from all this mess? And two, how do you do these asynchronous distributed snapshots so all the state is fault tolerant? Those two things are what was kind of the base of like why Flink is so interesting, I think.
So by that change, is it like now each event in the incoming stream gets annotated with the event time?
Yeah, and it's more than that too, because it drives Flink's operations by looking at the time in the data. But yeah, the data it does look at a timestamp in the data to figure out essentially what time it is. All right, so errors versus accuracy is the punchline. Failure handling, let's do this quickly. I think this is super important too, obviously. So to do this, the only thing I'm going to do different is rather than run it in my IDE, I'm going to start up a Flink cluster on my laptop, and then I'm going to build the same code we've been playing with. And I'm going to run that code on the cluster. Okay, this is what the Flink UI looks like, by the way. It's running one job. It tells you about resources it has in the cluster. It actually, we're not going to get into this right now, but Flink reads your program, which has got that nice sort of declarative API. It turns it into a job graph. A job graph is what Flink understands and knows how to execute at scale. So that's a job graph. That's our job graph. And so what I'm going to do now is cause a failure. And the way I'm going to do it is pretty brutal. I'm just going to like go and kill a task manager, which is where your kind of like the worker code runs. So this is exactly the same as like unplugging some machine. That's what I'm going to do. I'm going to kill -9. Okay? So Flink's going to tell you in a second it's noticed that that job is down. It's going to try to restart it. That's tunable, by the way. I have it set sort of high, so you can make this. I should fix that, but there. So Flink's noticed that that job is down. It's going to try to restart it right now. If you're running on Yarn or Mesos or something, it would have already been back up and running, right? Because it's a relatively small job. It would have been really quick. Right now, though, it's waiting for me. I'm like Mesos, or I'm like Yarn, so it's waiting for me. And the other thing is happening is we're not getting any data. That's not good. If we back up and look at more, you know, we've been generating data all along. I just zoomed out in time. So, you know, we had some interesting stuff going on, but then we kind of went down and we lost all this state, or we're going to lose all this state here. I can fire up a job now, or I'm sorry, I can add resources back to the cluster because I'm Mesos. And then Flink is going to figure out that it's got resources, and that job's going to start running again. And there it goes. It's producing data, obviously, but we've lost all this. We've lost our state, which is bad. And honestly, there's also like, look, there's that big gap in data. We don't want that either. We want to be able to we want to not be able to tell that there was a failure. Like, we want to be able to compute exactly the same thing as before, as if nothing happened. So all I'm going to do is turn on this asynchronous distributed snapshots algorithm that I talked about. There's never just to be clear, this is only a demo. You never run without this turned on. There's absolutely no reason to, right? And we can talk about the cost of it later, but basically you can do this without introducing really any latency, and it doesn't really affect, other than if the state grows really large, it takes some throughput on the network from you. But other than that, like, it doesn't really introduce any latency or anything. So that's kind of the cool thing about Flink. So if I run this again, I know we're out of time. Let me build the code with that one change. Flink list tells me all the running jobs. If you're not into the UI. Kill the currently running job. Submit the one just with that one line enabling checkpointing. Okay. Now we're at least back up and running, right? Because we submitted this job. Let me give you some interesting state. So the door 1, pressure 2, temp 5. Let's be crazy. Okay, so we're kind of running again. Maybe we look at the last 2 minutes. Okay, so we're in this state. Now, let's go and kill a task manager. Same things before. Holy crap, we're not getting any data. What's wrong? Big failure. And then, again, Flink is just waiting for resources. It's trying to restart the job. What we expect to see this time is that it's completely impossible to tell that there was ever a failure, right? All the in-flight state will come back. All the in-flight state will be picked back up. Think about this, like when I killed this thing, there's a bunch of windows just kind of in flight wherever they were. They should be picked up right in the middle, and just everything should just continue, and all of that. So now when I run,
This is a sick demo. You can tell us what's actually happening.
what's that?
Like, this is a sick demo. You can tell us, like, how it's actually doing it.
Yeah, I will. I swear. Okay? So there you go. That's complete stateful computation, even though we lost a machine for a while, and everything picked up just like it was before. Not even a blip. Like, imagine, these are all those windowed sums, right? Not even a blip anywhere. And those were all in flight when we failed.
The events were consumed at a later point of time, right?
What?
Event, because your task manager was down, the events were consumed at a later point of time.
What happened in a nutshell is like you're making these snapshots all the time, right? It's on some frequency. When some machine fails, you go back to basically the last good checkpoint. The whole thing just kind of ticks back to this consistent global state and just continues computing, right? So in a nutshell, that's what happened. And so when you tick back, the source operator is also stateful. So it just ticks back and it continues in a deterministic way to generate the same sequence of messages it would have the first time. So when you roll back sort of in the input stream, you also roll back the state to a consistent point. That's what gives you exactly once. That's what gives you this behavior. That's what exactly once means, basically in stream processing.
So that means it only once, like.
It's not message delivery. It's computing the same result as if each message was processed exactly once.
Okay, so.
It's a bit confusing, but those are the terms that have become popular in stream processing, unfortunately.
Delivery with an input and operation, right?
It's as if each message was processed exactly once. Each message is guaranteed to get applied to the state you're computing once.
Wait, so that means the source has to also be dealable, right? For example, like Kafka.
Yeah,
Otherwise.
exactly. I would say the source needs to be stateful. It needs to also be stateful. It needs to be able to return to a previous state and then continue.
The application of the state is idempotent.
In some sense, yeah.
In some sense.
Yeah, right. It's that if you end up processing one message twice, you've rolled back the state when you rolled back in the input.
Right.
So they go together. It's consistent,
Right.
right? That's why.
So for event time, when, like, if you drop a message that was somewhere in the middle of your previous processing,
Yeah.
does it like flip back to the old snapshot and then start recomputing?
Yeah. Yeah. And so here's the thing. The source, like this durability idea is not really, Flink doesn't really care about that. It's just that in this case, say you're reading from Kafka. The state of the source operation, the source operator, it's just a stateful operator like everything else. The state happens to be the offset in Kafka. That's all it is. So when it rolls back to a previous state, it effectively backs up in Kafka, and then everything rolls forward. So
What are the limits on this recovery? Like,
at the end, there's one more cool thing to like finish this sick demo. All right? There's one more cool thing. I swear, it's worth it. So now we're doing this. We're in this stateful. We're marching along. I want to do one more thing. Flink save point. And oops.
Just couple more minutes because there is a file.
Okay.
Central thing.
Okay. This always happens to me. Okay, Flink save point. What that is you just took a global snapshot yourself. It's built on the same mechanism, but you control this thing. Now we have this global snapshot. We can create as many of these as we want, and we can just keep them around. So what I'm going to do with this is I'm going to destroy the whole cluster, right? At this point, everything's down, of course, because we don't even have a Flink cluster, and like we're not getting any data. So think about this just for a second. There's not a Flink cluster anywhere. We don't have any machines. We don't have anything. But we have this snapshot. Let's say that we happen to have this data replicated into another DC, and say that, yeah, we have access to both to the input source like Kafka, and we have access to HDFS where we stored this stuff and it's replicated. So we move to a whole different DC, say. We spin up a new Flink cluster, maybe a new version of Flink, maybe a new version of your code, whatever. So start up a new cluster, and we say Flink run as before, but this time we're going to say from this save point right here. And then the same as before, run my code, and check this out. There you go. So there was a period of time when we didn't have a Flink cluster, and we just continued this whole stateful computation without a hitch. In the real world, that's important, because what you're going to do if you're going to upgrade your code, say, and fix a bug, is Flink make save point, stop your job, upgrade your code, Flink run from save point, and you just continue without losing anything. That's a production feature that is really hard to come. Without this, you can't ever claim to do like correct stateful computation over streams. You got to have it, because in the real world, you got to do this. Reprocessing, I said I was going to talk about, is the same thing. Just make save points every so often. And so like maybe I made a save point 3 months ago, and I say Flink run my job from save point, and go, and just use a bunch of machines. And it just rips through all the data again, catches back up to real time, and then you just continue processing. So that's it. For questions, we can do whatever. We can move to another room, but I think that's the end of the demo. That's